All right, so we're going to continue our lecture series, and today we're going to talk about a one sample t-test and interval estimation in principle, and then we'll move things along. Now, if you were to think about what we covered in our last 2 to 3 lectures, we talked about how you could use a z-score to test a null hypothesis. We could see whether or not the score is significantly different than one would expect by chance. We talked about going and finding the critical interval, right? So, or the critical value, better yet. And that's useful, right? So first you need to identify your p-value, right? And typically your p-value is 0.05, right? 5%. And you determine whether it is in the top 5 or bottom 5% on a one-tailed test, or top 97.5% or bottom 2.5% in a two-tailed test, to see if it was significantly different than one would expect, right? So we have to identify our p-value. Afterwards, we have to talk about the null and alternative hypothesis, whether the scores we obtained were significantly likely or significantly unlikely. And the biggest thing when we look at z-scores or z-scores for a sample, which was the last discussion we had, you need to know the population standard deviation. The problem is that sometimes the population standard deviation is not known to you. And what do you do if your population standard deviation is an unknown? Well, so here's what we do, right? So we calculate the standard error of the sample mean, right? So instead of the population standard error of the mean, there's a minor shift that it's going to be the standard error of the sample mean, right? So here we have the z-score x bar minus mu, the sample mean minus the population mean, divided by the sample standard error of the mean, which the formula is the same in principle. You have standard deviation divided by the square root of n. That is pretty much the same as what we did. The only difference, as you may recall from an earlier lesson on standard deviation, is that the sample standard deviation tends to be a conservative estimate, and we tend to remove, it's n minus 1, we tend to remove one of the participants to make it a little bit more conservative. All right. Now, so here we have an example. So let's say we had a college instructor who wanted to determine whether the average kid studies 12 hours per week outside of class for studying. And then he wanted to see whether or not that was true for her students. So she has 25 students, estimate how many hours they study during a typical week. So mu, which is the average population studying, is 12, but x bar, in her case, her students are only studying 10, with a sample standard deviation of 3. The question is whether or not these kids or students are studying significantly less than the population. So we could actually, before I get to that, we can actually calculate that. So let me go back to the board and demonstrate how we would calculate that. So I'm going to stop the share for a second, and I'm going to set up the board. All right, so here we are at the board. Let's write our characters at the top. I'm sorry I'm not in frame. I'm trying different views. So we notice mu was 12, right? We notice that x bar right, this teacher's sample studied 10 hours. We noticed that the number of participants was 25, and we noticed that the sample standard deviation was 3. All right, so based on this, we should actually be able to calculate our formulas. So if we do this, we're going to do standard error of the mean first, right? So we're going to do 3 divided by the square root of 25, right? So that's our standard error of the mean. And that's going to be 3 divided by 5, which gives us 0.60. Now, so I have my standard error of the mean. And then in order to calculate the z-score, what I'm going to do is 10 minus 12. And when I do 10 minus 12, I get -2 on the top. I get 0.60 on the bottom. And then we have to calculate that z-score. So let me get a calculator and I will tell you exactly what that comes out to. All right, so here I have my calculator. So I'm going to do -2 divided by 0.60, and I'm going to get a number -3.333. So that would be the final solution here. And then the question is whether or not these students are studying significantly less than the population. So the first thing you're going to do is set your alpha, all right? Your alpha was 0.05, right? So then you're going to do the null and alternative. Null is X bar is equal to mu. I don't know if you can see that. The alternative is X bar is not equal to mu, right? Then we have to decide whether we're doing a one-tail or two-tail test. So in this case, we're going to do a two-tail test, which means that the critical value is going to be plus or minus 1.96. So number 5 is to actually calculate your answer. So our obtained value is -3.33. And now we have to make a decision. Are we going to accept or are we going to reject the null hypothesis? The general principle is that if the obtained score is equal to or greater than the critical value, then we will reject the null. So in this case, we reject the null because -3.33 is greater than minus 1.96 in the negative. So -3.33 is more negative than minus 1.96. So the final thing is we interpret this, and I don't have enough space on the board to write it, but we would say using a z-score for a sample, we found significant differences in the amount of hours studied in a sample relative to the parent population. More specifically, the students in the sample studied significantly less than the overall population. So notice when I do this interpretation, the first thing I'm going to do is identify whether there are significant differences. I state what the test was, the z-score for a sample. And then I look at the means, right? So this is the sample mean, this is population mean. The sample mean, they did significantly fewer hours than the population mean. And that is how we would do a z-score for a sample. And I'm gonna press pause and reset the slideshow, and then we'll continue with the one sample t-test. So in this case, this professor, they found that their students studied significantly less than the parent population. Now, that's a z-score for a sample using this sample standard deviation, which is interesting because here we go again, a t-distribution, this is a one sample t-test, the formula is the same. So I kind of wanted to show you a morphology, right, between what we started out with a z-score to a z-score with the population and the population mean and standard deviation being known to a z-score for a sample to a t-distribution, which the change is that now we're using the standard error of the sample mean. Okay, so in terms of assumptions of a t-test, we assume that a t-test is normally distributed, bell-shaped, right? We assume that it's symmetrical. We assume that it's asymptotic. And we have a mean score of 0. Now, t-distributions tend to be a little bit flatter than z-distributions. That's important to understand. And the reasoning for that is that it's more of a conservative estimate. If you had all of the individuals from a population, you could have a perfect shape. But as you have fewer numbers, it gets flatter, right? So that's just one of the principles. Now, we assume that our t-distribution is symmetrical and normally shaped, but that doesn't necessarily mean that it actually is. We can test our t-distributions for skew. We can test our t-distribution for kurtosis, but the assumption, although it could be violated, is that we have a normal distribution. Now, that only occurs, or we start to see an approximation of a normal distribution when we have roughly 25 to 30 participants. So in terms of the t-distribution versus the normal distribution, typically you're going to need a larger critical value to reject the null when you have a t-test versus a z-score. A z-score, you have all parties of interest. In a t-distribution, it's a sample, right? So in general, the critical value for t tends to be larger than the critical value of z to reject the null. Now, what we will notice, though, is that as the sample size gets larger, we start to see z and t get closer and closer together. So the critical value for z, as we saw, for a two-tailed test is 1.96 plus or minus. And for a one-tailed test, we said it was 1.65 in the same direction of whatever our hypothesis was. Now, if you have a sample of 100 or more, then the difference between a z-score and a t-score is fairly negligible. Now, but I do want to take the book. I want to show you the T-table chart. So let's see if we can find with degrees of freedom. Now, I haven't defined degrees of freedom yet, but typically it's n minus 1 or n1 plus n2 minus 2 in an independent sample t-test. But so our degrees of freedom is whatever our sample size is minus 1. So if we had 25 participants in that, or students in that previous study, we would say n is 25 minus 1, which is our degrees of freedom, would be 24. And then we would go down the column, I don't know if you can see, until we find the number 24, right? And then we would go across the top based on whatever our p-value or alpha we were looking for was. All right, so that is in your table. I recommend in the older version of the book, it's table C or appendix C. In the newer versions, it's in appendix B. All right, now what do you do if you have a sample size that is in between two numbers on your table? So if you look at the table that I just showed you on the screen, it goes 1 through 30 and then skips the 40. So what happens if you had a sample size of 35, which means you have degrees of freedom of 34? Well, the general rule is that we go up, not down. So we would go to the more conservative critical value for 30 degrees of freedom. Now, when you're using SPSS, it actually calculates it more precisely. But using the back of the book in these tables, we have to be conservative so that we don't incorrectly reject the null hypothesis. Now, so as I said, degrees of freedom are the number of scores that are free to vary from a constant. So the way I think about it is, let's say we had that sample of 25 and I was a member of that group. How many people in the sample are not me? How many people are able to vary from me? So we're looking at number of scores that can vary from a constant. So if I had 25 people in the sample, then there would be 24 other people that are not me, right? So that's how we do it, n minus 1, right? So, and it's useful, right, to see spread of scores and determine how that goes. Now, you may recall when I showed you, if we go across the top of the book, now I'm going to try and see if I can make this bigger for you. We go horizontal, right, across the top. That's going to tell you the criterion of significance. Remember our alpha, if it's 0.05, right? 0.01 if it's more stringent, lenient 0.10. I think we talked about that. That's across the top, right? Now you'll notice that it has a value that's for one-tail test and two-tail test. And then when we go down the side, you can see the number of degrees of freedom. Now, what I'm going to do is because I'm actually fairly small on the screen, let me do it this way. This is probably easier for you to see, right? So you'll see the level of significance at the top. And at the top, this is one-tailed. The one below it is two-tailed. And then going down, you'll see the number of participants. It goes here, right? But it's degrees of freedom. That means whatever your sample size is, you're going to subtract 1 from it. So if we had 25, we're going to go to 24, right? And then we would go across to match our degrees of freedom with the number of tail tests we had and our alpha, and that would become our critical value. Now, what's interesting is that if we go for a two-tailed test and we had an infinite number of participants, we have 1.96. So remember how we said earlier that when we have a over 100 participants, the difference between Z and T starts to get negligible? Well, if we had an infinite number, the Z and T would be identical, right? But typically, if we had an infinite number, then we would have the population, right? So, but in any event, as we get a larger sample size, Z and T start to approximate one another. So that is how we look at critical value. So you go across the top to find what your alpha is, and based on the number of tails you have, and then you go down based on your degrees of freedom to get your critical value, right? So in general, as I said, how do we determine whether we're going to accept or reject the null? If your T statistic is less than the critical value, we accept or retain the null hypothesis. If your T statistic is equal to or greater than the absolute value of the critical value, then we would reject the null. Now, in a one-tailed test, the sign must match. In a two-tailed test, the sign does not matter because it's plus or minus. All right, so just to give you a more comparison, if you were to compare a T distribution relative to a Z distribution, you generally would need a larger critical value for T relative to Z, right? So if you had a sample of 10, a Z score, the critical value would be 1.96, whereas a T score would be 2.26. But as the sample size increases, your T critical value actually drops. So if we look at the second bullet point, if we were to move our sample from 10 participants to 60 participants, our T critical value would be 2.00. And that comes from the back of the book, if you're wondering where the numbers came from. Whereas our T for 10 was 2.26, right? So it's getting smaller and smaller and closer to the Z. When we have 120 in the back of the book, you'll see that the Z always stays 1.96 because that's based on area under the curve and percent of scores to the right or to the left of the middle, the two tails. If you have 120 participants, now you see that it's 1.96 for the Z as always, but the T score goes down to, the T critical value goes down to 1.98. And then I showed you that if we had infinite degrees of freedom, then it would be identical. All right, so here's another example where we might have to calculate. So if you have a population mean of 27.31 on a test, but you don't know the population standard deviation. And because you don't know the population standard deviation, you're going to use a one sample t-test, right? You know that your class scored an average of 29.07 with a standard deviation of 9.48. So the instruction is to compute a t-test for significant differences. So I'm going to pause the lecture, set up the board for our one sample t, and we're going to go from there. Okay, so I have everything set up. So I have my one sample t-test. T is equal to x bar minus mu divided by the sample standard error of the mean. Standard error of the mean is the sample, standard deviation divided by n. From the previous slide that we went through, these are the 4 bits of information we need to know, right? So our sample, our population mean was 27.31. Our sample mean was 29.07. Our sample standard deviation was 9.48. And our sample size, which I realized was not on the slide, but you need this. You need a sample size. So we're going to keep it as the 25 that we've been discussing through and through. So here we are. So we're going to go through the steps, right? So actually, I'm going to say decision is here. I added something so we can actually follow the logic and then interpret. All right, because it's a t-test, we have to find our degrees of freedom. Now I kept the alpha or the level of significance at 0.05 because that's standard alpha. I kept it as a two-tailed test. Degrees of freedom, you may remember, was n minus 1. So when we look at our n is 25. So that would be 25 minus 1 or 24 degrees of freedom. So now I need to go get my critical value. And I'm going to move this for a second because the book is holding the computer for now. So I need to go to the back of the book and find the critical value for a two-tailed test, level of significance, with 24 degrees of freedom. And the critical value that I come up with is 2.064. 2.064, that's my critical value. Now, if you're wondering where that came from, just again, if you look at the book and you go across to 0.05, sorry, this is hard to do with the camera angle. So we go level of significance for a two-tailed test, 0.05, and then down to 24. If we go down to 24, you see that it's 2.064. All right. So now I'm ready to calculate. I'm ready to crunch my numbers and see what I find. So, all right. So let's do, I always like to do my standard error of the mean first because that's the denominator. So we're going to put 9.48 divided by the square root of 25. And so that's 9.48 divided by 5. So let's calculate that. 9.48 divided by 5. I get a standard error of the mean of 1.896. So that's the denominator. So that's standard error of the mean. Now, when we do the one sample t-test, we do x bar minus mu divided by standard error of the mean, right? So when we're doing this, we're going to say x bar is 29.07 minus mu, which is 27.31. And that's going to be divided by our standard error of the mean, 1.896. So let's calculate this out. So we're going to say 2.907 minus, take that back, 29.07 minus 27.31 gives us a numerator of 1.76 over 1.896. So let's calculate that out. 1.76 divided by 1.896 gives us a final calculation of 0.928. So that was our t-value. So we're going to then take that 0.928 and we're going to decide to accept the null. H0 is the null. Now, why do we accept the null? Is because 0.928 is less than 2.064. So now we interpret it. So now I've gone through all of the logic, right? My alpha, or level of significance, number of tails. I calculated my degrees of freedom. I went to the back of the book, found the critical value, calculated my t-value right here. And then because 0.928 is less than 2.064, we accept the null, which means that using a one sample t-test, we found no statistically significant differences between our sample and the population. That's how you do a one sample t. So you'll notice this lesson is not all that different from the previous lesson, right? So the formulas are virtually the same. We're just using a sample standard deviation versus a population. So let me pause this and get reset up. Right, so when we computed the t-test, we did not find that our group differed statistically from the population. So that's important. All right, so let's continue. Now, for the rest of this lesson, I'm not going to make you calculate it, but I do want you to know what interval estimates are, right? So these are usually above and below the mean, and it allows us to tell roughly how certain we are that a given score, if we were to have a population, this score would be found in that population. So an interval estimate allows you to say plus or minus. So the best way to describe this is, let's say a person had an IQ of 100. And I said that using an interval estimate of plus or minus 6. Well, what would that mean? That would mean that we believe that this person's true intelligence is anywhere between a 94 to 106. How do you get that? You take the 100 plus 6 minus 6, right? So that allows us to understand. Now, there's something called a confidence interval. And here's the deal. You want to have a confidence interval of 95% or higher, because that is your level of certainty, right? So we talked about the plus or minus scores, but the confidence interval is your level of certainty that the score reflects the true ability. All right, here would be the formula. You take the mu and then you take minus the t-value times standard error of the mean, and then you have your mu, whatever it is, and then you do the same thing plus. So the reason why you have plus or minus a given score is because the formula is the same on both sides of mu. All right. So in terms of confidence intervals and null hypothesis testing, confidence intervals can be used to estimate a population mean if we had to, or to test the null hypothesis, right? And then obviously this gives us more information as we do hypothesis testing. Now we also have standard error of the proportion, right? So this is a calculation for a z-score formula, standard error of the proportion. It would be P, which is a proportion, minus whatever the hypothesized value of the population proportion would be, divided by the square root of that hypothesized proportion, times 1 minus that value, divided by n. So it's very similar to our standard error of the mean formula, but it's for a population. All right. Here's an example of confidence interval for a proportion. So notice if it's a z-score proportion, It's 1.96 times the standard error of the proportion, right? Whatever it is on the minus side, whatever is on the positive side. So that, in a nutshell, is this week's lesson. So I'm going to stop there, and I hope this was somewhat useful to you.